Okay, so right, let's continue our maths lecture with the next topic, which is the differential equations. So at the end of this week, you should be able to identify the types of differential equations and develop strategies to solve first order ordinary differential equations. Okay, so why do we need to learn about differential equation? Because in creating the mathematical model of a physical system, we frequently involve these three types of equation. We may have to deal with differential equation or integral equations or integral differential equation. So the example of these equations can be seen in your notes. Okay, so we need this equation to express the relationship between the quantities of dependent and independent quantities or variables. Right, so let's take an example related to chemical engineering instead of the one in your notes, which shows an example for electrical engineering. But here we talk about the model development of a CSTR. So CSTR is a continuous third tank reactor, where you will learn about this further in reaction engineering 1 in your second year. Right, so yeah, this is your CSTR tank. So you have this buffle to mix the mixture inside the CSTR tank. So it's for liquid mixtures, liquid reactant and product. So let's say you have this reaction A produces B. So A is the reactant. So assume first order reaction A produces B, where K is the reaction rate constant. Okay, and yeah, you can label your flow rates or just inlet and outlet. So here is your inlet, Fi. I refers to initial or input, and the concentration of component A in the inlet is CAI. And then inside the reactor, you have this volume of the liquid and concentration of A and concentration of B, noted by CA and CB respectively. And at the outlet flow rate is FO. FO. O is for outlet, and CA and CB is the same with what is inside the reactor here, because assuming it's already reaching a constant, steady state. Okay, steady state. Okay, so assuming constant density, we can do a quick mass balance. Okay, quick mass balance on component A and in the overall mass balance. Okay, so assume constant density m equals to rho v. So when we assume rho is constant, the left hand side and the right hand side, then you can just eliminate the rho. So we can do our mass balance in terms of volume, but in this case, it's just the volumetric flow rate of the liquid. It's not really the volume balance, okay? Just bear in mind. Okay, so dV over dt, the change in volume per unit time equals to Fi minus Fo. So here is let's go through the component balance for A. Right, so looking at just component A, the inlet flow rate of A is Fi times CAI. Okay, so CAI is the concentration of A, and the outlet flow rate of A is FO times CA, and rate of consumption of A is given by the reaction, because we have the reaction A produces B, where K is the rate constant. So rate of consumption of A is K times CA times V, because here our concentration is mole per unit volume times volume, then we have the number of moles as the absolute unit for the mole of A consumed. And also we have this rate of accumulation of A, dCAV times dt. So this will give you the mass of A accumulated in terms of rate, okay? Mass of A accumulated per unit time. If it's steady state, then it's 0, but let's just derive the general balance equation for component A in a CSTR. So let's continue. So, from your mass balance in CPP1, the general mass balance equation is that input equals to input minus output plus generation minus consumption equals to accumulation right? So in this case, there's no generation of A because A is a reactant, so it's just consumed. So that's why you can get this equation here, where accumulation equals to input minus output minus consumption. So what you do is you just key in all those terms that we have defined in the previous slide here. So you just put it in. So this is your input, this is your output, this is your consumption term, and this is your accumulation term. Right. So here you can break it down into two derivatives because this is a product of two variables. So you can take out V dCA dt plus CA dV dt and equals to the input minus output minus consumption. And this dV dt, you got it initially from this general mass balance here. So you put that dV dt inside here, then you get dV dt equals to Fi minus Fo. So you can rearrange to get dCA over dt, a change in the concentration of A per unit time, equal to Fi over V times CA minus CAI minus CA minus the KCA. So, well, here the goal is to just illustrate to you, give you an example of how do we use a differential equation to describe the mass balance of a reactant A in a continuous stirred tank reactor CSTR. So this is a differential equation, right? Okay, so there are some examples of fundamental laws which you can write in the form of differential equation. For example, here you can see these are all taken from your notes. So first one is Newton's second law of motion. So you know Newton's second law of motion, you can write it down as F equals to ma. So F is, okay, well, right, you can write it as in terms of this expression, because A is actually the change of velocity per unit time. So A is equal to dV dt, where V is a function of t. So you have the dV as a function of t, and force and over mass. So here you can write down A equals to F over m, where you can write it in terms of differential equation like this if you want to have a more dynamic function of velocity and time instead of just an absolute value of A and F and M. Okay, so the other example include Faraday's law. So this is the voltage drop across an inductor. Not too familiar with electrical terms, so we'll proceed with the Fourier's law for heat transfer. So Fourier's heat law, this one you will learn in heat transfer in second year. So Q here is the heat flux going through something, a slab of solid, for example. Okay, so the heat flux equals to minus K. K is the thermal conductivity, so it can be considered a constant, and times dt dx, the change of temperature with respect to x. X could be the distance or the length of the solid slab or something, okay, of which the heat is diffusing through. Then the next law that you can write in the form of differential equation is the Fick's law of diffusion. So diffusion of gas, for example, into air. So it can be written as J is a mass of flux equal to minus D. D is the diffusion coefficient times dC over dx. So C here is the change in concentration with respect to x, the distance traveled by the gas. So you can see here from Fourier's law and diffusion, Fick's law of diffusion, it's the driving force. Here in this case, driving force for heat transfer, driving force with respect to the length of the solid. So this is your resistance, driving force per resistance. And for heat diffusion as well, the driving force is the change in concentration. So the gas transfers from higher concentration to a lower concentration. So CAI and CA. So CAI must be greater than CA in order for there to be a flow or for a change in concentration. Otherwise, there will not be a diffusion. So that's just to give you some example related to what you're gonna learn in the later years using ODE. So why do we use differential equation? So it gives us empowerment to make precise prediction about the behavior of our models or system, because we don't just have an equation, but we have a differential equation with respect to something. Okay, with respect to time, with respect to the length, with respect to the distance. Okay, so we just we can know how the variable behave with respect to the dependent variable. Sometimes if we can't even completely solve the differential equation, we can still determine some useful properties about the solution, because we know how it behaves. When it reaches a certain point, will it increase or decrease? So is it changing linearly or exponentially or quadratically? So it's useful. So you can further read these appendices 11.1 and 11.2 in your notes for you know, to satisfy your curiosity for further reading. Right, so next is the terminologies of differential equations. So these are the things that you need to be well conversed with. So we'll go through one by one. So there are 6 terms that you need to be familiar and know what it means. The first one is for you to be able to identify and define what is independent and what is dependent variable. So dependent variable is the variable or variables that is differentiated against, whereas independent variable is the variable or variables with respect to which differentiation occurs. Okay, let's see an example here. I mean, 2 examples here. So in the first equation, you have the 2y over dx squared minus 4x times dy dx equals to cos 2x. So what would be the dependent variable? So the dependent variable is the variable that is differentiated. So you differentiate y. So the dependent variable in this case is y. Whereas the independent variable is the variable with respect to which differentiation occurs. So you can see that in this equation, differential equation, it is being differentiated with respect to x. So independent variable is x. Okay, so y is a function of x. Y is dependent, where x is independent. And then look at the second example here, d2x over dt squared minus 4x times dx dt equals to cos 2t. In this case, x is now the dependent variable, and the independent variable is then t, because t is, the independent variable, which will define the value of x. Okay, next term is for you to distinguish between ordinary differential equation ODE versus partial differential equation PDE. Okay, so the classification of ODE and PDE depends on the number of independent variables regardless of the number of dependent variables. So ODE are equations that involve ordinary derivatives, okay, i.e. the full D symbol. Okay, it has only one independent variable. Okay, so one independent variable, but it can have many dependent variable, but independent only one. And it can be identified either as an ODE problem or a system of ODE problem. Okay, let's see an example here. For first example is the brine mixture problem. So X is the concentration of salt, the concentration of brine, and T is the time. So you can write down the change in concentration of salt per unit time, and this is the function. So 2 minus x over 5. So in each case example here, so think about what are the dependent and independent variables in each example. Okay, so the next example here is a system of ODE problem. For example, population of rabbit and fox, where X is the population of rabbit and Y is the population of fox per unit time. So you can write this dx dt, the change in the population of rabbit per unit time, and the change of the population of fox per unit time, because fox eat rabbits. So if there are more rabbits, there could be more foxes. Or if there are more fox, then the population of rabbit will decline sharply over time. yeah, vice versa. So the population of rabbit depends on the population of fox, and the population of fox also depend on the population of rabbit. So if there are no more rabbit in that place, so maybe the fox has to migrate, and maybe the population of fox will also decline because of starvation. So, you know, this is a system of ODE problem which will give you the interdependency of each variable. So x is dependent on y, and y is also dependent on x, but t is independent. Okay, so you can see, you can identify that for ODE and PDE, the definition depends on the number of independent variables. Okay. Next, okay, PDE. So PDE, the easiest way to spot a PDE and not confuse it with ODE is the curly D symbol. So this is the partial derivative symbol. It has two or more independent variables, can also be identified as either PDE problem or a system of PDE problem. So example here is the transient heat equation. So the change in temperature per unit time depends on the time, and also depends on the length or the thickness of the solid at which the heat is being transferred to. So this is one example. And another example is the Navier-Stokes equation for flow in incompressible fluid in a pipe. So you will learn this in fluid mechanics 1 or 2. Okay, so here U is the flow velocity. So the velocity of the fluid depends on the time and the x, the distance traveled. Okay, so in PDE, you have two or more independent variables, and you have this partial derivative or the curly D symbol. So you can think of, for each example here, what are the dependent and independent variables in each example. Right, the next terminology that you should know is the order of the differential equation. So the order of a differential equation is defined as the number of the highest derivative that occurs in the equation. So okay, let's look at the ODE first. So let's have a look at ODE. So example 1 here, so 4 dx dt minus 3 dy dt minus x plus y equals to cos 2t. So what would be the order? So you look at the highest derivative. The highest derivative is dx dt dy dt. So it's just the first derivative, and the order, so the order is 1, first order. Okay, so next example is still in the ODE column. Dx dt squared minus 3 dy dt minus x plus y equals to cos 2t. Here, look at the derivative. It's still in the first derivative, so it's first order. Okay, number 3, example 3. Yeah, d2f over dx squared minus 4x df dx equals cos 2x. So here, the highest derivative is the second derivative, thus the order is 2. And number 4, yeah, you can see here, so the highest order is second derivative, this is first derivative, so the order is 2. Okay, so do not confuse degree with order. So the degree refers to the power of highest order derivative, whereas the order refers to just the level of derivative, first derivative, second derivative, third derivative, and so on. Okay, next look at the PDE. So similar to ODE, we look at the number of highest derivative that occurs in the equation. So as you can see for the first one here, it's the only involve first derivative. The second one also involve only the first derivative, so both are first order, whereas the third one you have second derivative, that's the second order, and the fourth one, it has a second derivative, that's the second order. So here it's just the degree. It doesn't have anything to do with the order of the differential equation. Okay, so example 1, look at the types of ODE. So for each of the ODE, for each DE differential equation below, indicate if it's a ODE or PDE and of what order and what degree. So look at the first one. Okay, is it an ODE or PDE? So since this is a recorded lecture, so I'm just gonna answer my own question. So this is ODE because it only have one independent variable, which is t, and then what order is first order, and of what degree? Is a second degree. Okay. Number 2 is obviously is a PDE because of the curly D, and also you have 2 independent variables. And what order? Second order, because it involved the second derivative here. And of what degree? So look at the highest order and what degree. So the second order only is up to the power of 1, so it's still a first degree or the PDE. And the third one is also a PDE and first order and fourth degree, because both are first order, but this one's got the power of 4, so it's a fourth degree PDE. Right, so next is for us to distinguish between linear and non-linear ODE. So, okay, how do we differentiate or distinguish between linear or non-linear? So in general, we have to write the ODE in the standard form here. So let's say it's of the nth order. So write down a to the n as a function of x times y to nth derivative plus a minus a n minus 1 x y n minus 1 and so on and so on. Okay, so until the second derivative you have a2 and second derivative of y, a1 first derivative of y, a0 and just y, and finally you write at the right hand side the function of gx only. So a sub I as a function of x here is a function of the independent variable x. In this case it's x, but it could be any other number, or it can be y, it can be t, it can be whatever, as long as it's the independent variable. Okay, and the I starts from 0, 1 until the highest order that is involved in the ODE. Gx at the right hand side here is a function of the independent variable. In this case it's x, but it could be anything as long as it's an independent variable. And y in this case is the dependent variable. So by default, just y is dependent and x is independent, but it could be the other way around, and it could be some other letters. Okay, not just x and y. And looking at non-linear ODE is any ODE that does not follow the linear format is a non-linear ODE. So for example, here you can see if you try to rearrange and it does not fit into the standard form, then it's a non-linear ODE. And also, if you see anything that, let's say here a sub n is a function of both x and y instead of just x, so it's non-linear. And if you see the derivative to the nth order and it's raised to the power of a, where a, b, c and d here is not equal to 1, then it's non-linear. Okay, so for anything, the derivative that is raised to a degree of a, b, c, d not equal to 1, then it's non-linear. And if the function a involves more than one variable, involve both x and y, both independent and dependent variable, then it's non-linear. Okay, as simple as that. Right, so for each of these ODE, let's try to indicate whether the ODE is linear or non-linear and compare them and see what order and identify the dependent and independent variable. So let's do that. So the first example. Okay, let's try to take this one. I'm just going to copy this and put it on whiteboard so that it's easier to scribble around. Oops. Okay, right. So first example, you want to compare with the standard format. So the standard form is, let me copy. Yeah, this is the standard form for the linear differential equation. Okay, so you want to compare with this form. Oh, I just want to write this here. Okay, so then let's try to do one by one. So let's do for number 1. minus 4 dy dx minus x squared equals to 0. So you can see that this starts with a1 here because it's just first order. First order. So you can write down, and this one is 4. Wait. Okay, just compare this with a1 y prime minus a naught y equals to gx. So you can write this down for dy dx equals to x squared. So you can compare it with the standard form. So you can identify that a1x is -4 and y prime is dy dx. A naught x is 0 and y is also 0 and gx is x squared. So you can identify with all of the terms in the standard linear form. So thus the first one here is linear. Okay, what order is the ODE? Is first order. And identify the independent and dependent variable. So independent is x and dependent is y. Okay. Okay, so try to do the next one. Yeah, got it. Okay, so try to do the next one. Number 2 is d2f dx squared minus 4x df dx minus cos 2x minus 3 equals to 0. So here your independent variable is x and your dependent variable is f. So you want to write down the standard form into dependent and independent variable. So it starts with the second order. So you want to put a2 as a function of independent variable x times f double prime plus a1 x f prime plus a naught x f equals to a function of x gx. So you compare this with this, the standard form, so you can identify which one is which. So a2x here is equal to just 1. And then, oh no, let's just rewrite this. Oh no. I just want to erase this part and this part. So let's rearrange this into d2f dx squared minus 4x df dx equal to cos 2x plus 3. Then you can compare this with this to see which one is a2, a1 and a0, so that you can identify whether it's linear or not. So here you can see that d2f dx squared is f prime, so a2x is 1. Then a1x is -4x and this df dx is f prime. a0x is 0, f is also 0, and gx is this one, cos 2x plus 3. So this is linear. Okay, this is also linear. What about the number 3 example? Okay, let's do number 3. So here you have the third order, d3x dt cubed plus 3 dx dt plus 2x plus cos t equals to 2. So here your dependent variable is x and independent variable is t. So you want to write, because this is third order, so you put a3 as a function of t, x triple prime plus a2 t x double prime plus a1 t x prime plus a naught t x equals to g of t. Then you want to rewrite this equation such that you can compare with the standard form. So for d3x dt cubed plus, there's no second derivative, so just put here 3 dx dt plus 2x equal to 2 minus cos t. So can you compare with the the standard form here? So you can see that a3 is 4, this one is x triple prime, this whole term here is 0, and a1 is 3, dx dt is the x prime, and x is x, and a naught t is 2, and gt is this. So you can compare with every term, thus this one is also linear. Okay? Right? Yeah, continue with the next example, number 4. Okay. Number 4 is negative 4 dy dx squared equals to x squared. Well, from here you can already see that it's nonlinear because this dy dx term is raised to the power of 2, thus it's a nonlinear. You don't have to even compare with the standard form because you're never going to get it. So just bye-bye, nonlinear. Okay. Oops. Next one is number 5, example 5. So d2f dx squared minus 4f df dx plus cos 2x equals to 0. Dependent variable is f, independent variable is x. So you want to compare with, okay, starting from the first derivative, second derivative, a2 as a function of x, f double prime plus a1 x f prime plus a naught x f equals to g of x. All right. So okay, let's rearrange this so that you can compare with the standard form. F dx plus nothing equal to cos 2x. Yeah. So okay, here you can compare. This one is this one. F double prime is d2f dx squared. So a2 is just 1. F prime is df dx. But is this the same with this? So here is the nonlinear component, nonlinear part of the ODE, because you're supposed to have a1 as a function of x, but here you have a function of f. So this is the part where it is nonlinear, right? So here is okay, everything is okay, but once there is one part where it is nonlinear, thus the whole thing becomes nonlinear. So number 5 here is nonlinear. So is number 4 here nonlinear? Okay, so yeah. Last one, last example, number 3. Number 6. Okay, so number 6, 4 d3x dt cubed plus 3 dx dt plus 2 sine x plus cos t equals to 2. So you want to compare with the third derivative, a3 as a function of t, because t is now the independent variable. X triple prime, a2, x double prime plus a1, x prime plus a naught as a function of dx equals to g of t. Right, okay, so I think you can start to compare already. So here is your third derivative, and 4 can identify with a3. There's no double, so here's 0. So first derivative is this, and 3 is this. However, do you have an x here? No, you don't have an x, but you have a sine x. So that is the nonlinearity component, nonlinear component. Whereas gtx, you can write it down as 2 minus cos t. So this one would identify as gtx. However, the problem here is your x, because you don't have just x as a function, but you have sine of x. thus it is non-linear. So number 6 is also non-linear. Right, so now I hope you can identify what is linear and non-linear functions for ODE. Where were we? Yeah, here, right. Okay, so some general observation for linear and non-linear ODE. So most of the time, the non-linear ODE has the non-linear components such as the coefficient A in function of both independent and dependent variable, or if you have the derivative, it's raised to the degree more than 1. Okay, so if you have y to the power of 2 and dy dx to the power of anything greater than 1, then it automatically become non-linear. For linear differential equations, there are no products of the dependent variables and its derivative, and neither the derivative occur to any power other than the first power. And many of the nonlinear equations that occur in engineering cannot be solved easily as they stand, but can still be solved for practical purpose, because engineering involves practical solutions, not just mathematical solutions. So if we cannot solve them analytically, we will still find ways to solve either graphically, numerically, whatever ways, as long as we can approximate the solution at least in our region of interest. Okay. Right. The next part is to see the difference between homogeneous and non-homogeneous linear DE. So now we are just focusing on the linear differential equation, but we want to know whether the linear differential equation is homogeneous or non-homogeneous. And this method is applicable for linear differential equations only. So how do we classify the linear DE into homogeneous or non-homogeneous? So first, we need to arrange in the standard format, where all the terms containing dependent variable will be on the left-hand side, whereas all the terms containing only the independent variable and constant will be on the right-hand side. And then we compare. If the right-hand side equals to 0, then it is homogeneous. And if the right-hand side is not equals to 0, then it is non-homogeneous. So here are some examples how to see whether it's homogeneous or non-homogeneous. So this is the standard format for linear differential equation, as we have seen and used to identify whether it's linear or not. Okay, so here you can see for some examples of homogeneous DE, where you have this, and the right hand side equals to 0. So here x is the dependent variable, t is the independent variable. So at the right hand side, there's nothing about the independent variable and no constant, so it's 0. But if you have here dx dt plus 4x equals to 5, then because of this 5 on the right hand side, it becomes non-homogeneous. Okay, so yeah, the idea is to arrange in the standard linear format and see if the right hand side is equal to 0 or not. But you don't purposely put everything on the left hand side to make everything on the right hand side equals to 0. The idea is to follow the standard linear format and really see if the gx here, there is none representing the term gx here. Okay. So this is actually out of scope in this lecture, but if you want, you can read on to in the appendix 11.3, same with this one and same with this one. Okay, next we're going to talk about solution to differential equation in the next video.